Welcome everyone, I'm software engineer at Microsoft and today we are in the office and we are solving LeetCode problems. Today's problem is product of array except self. So here we have input array and we need to produce some output array which fulfills this requirement. So every element of the output array is the product of all elements in the input array except the element at this index. So for the first index it will be product of all elements except the first element, 2 times 3 times 4. For the second one, it will be 1 times 3 times 4 without 2. For the third one, it would be 1 times 2 times 4 without 3, and so on. So the naive approach would be to traverse the whole array, picking one by one, and then do additional for loop that would calculate the product of every single item except the current item. With brute force, the complexity time would be n times n, which is n squared, because we are traversing array here, and for every possible index, we are traversing array again. Still, the space is constant if we don't count the result array, but it's not good enough, and we are getting time limit exceeded. But these LeetCode mother trackers gave us already the constraint that it should be all-when solutions, so two nested for loops are not good enough for us. And we also cannot use division operation. However, the division operation solution for me is a bit trickier than the optimized solution. So let's break down the problem how we can do it faster than n squared. So this is the product of all the numbers of our input. These are the indexes. So every time we need to calculate product of all the items except the currently selected item. For index 0, it should be this product. 2 times 3 times 4 and so on. For second one, it should be same product but without 2. With the division operation, we could just divide by 2, so we can the whole product, let's say we are at index, 2, we can divide this product by 3 and we will get exactly our product. But we cannot do it according to the description. So for every index, we're just gonna remove it and leave the product as it is. For some specific element on the array that we want to remove, what does this product look like? It looks like two separate products that should be multiplied together. And it happens for every possible index. So let's say we are putting it back and we take off the 3 and it is the same product of these two multiplied by product of these 3. So it means while we are moving from the left to the right, we would have a bunch of these products, and each of these products is basically based on previous product. What do I mean by that? Whenever we at index 4, for example, and we already have calculated this prefix, while we are moving to element 5, we already calculated this prefix. We don't need to recalculate it again. We need to just take this prefix, multiply it by 4, and it will be our new prefix. Same thing happens when we move to element 6. Previously we had this prefix calculated already, and new prefix is just this prefix multiplied by previously computed element, which should be this prefix. So it seems like we can calculate every possible prefix, this, and that. And this way we can access the left side product just in constant time. The same applies for the suffix. Whenever we take some element, we want to know this product, and this product exactly will be used to calculate the next suffix when we calculate this element, for example. So the suffix would be previous suffix times previously calculated element, and this will be our suffix. If we also can pre-calculate all the possible suffixes and then use it as a constant time. With this approach, we would have just 2 for loops to pre-calculate prefix and suffix, and then 1 traversal to calculate the output. In this case, our prefix and suffix would look like this. So whenever we at some index, let's say at index 3, what we would need to do is to take prefix at index 2, which is this one, 6, and suffix at index 4, this one. And together combine, we just do multiplication, and this will be our result for index 3. The prefix and suffix solution gives us a bit better complexity. So we are traversing input array 3 times to calculate the prefix, to calculate the suffix, and to calculate the output. The space here is not constant. We are using 2 times n space because we need to store prefixes with size of n and suffixes with size of n as well. Let's not consider output as a space complexity. Now let's think a bit more about the prefix and suffix approach. Whenever we at element 5, let's say, do we really care what was the prefix for element 2, for element 3, for element 4? Actually, we don't anymore because we already processed these items and we already put them to output. So we don't need to maintain this prefix, that prefix, that prefix, and we only care about this specific prefix to calculate the 5, which we haven't calculated yet. Same applies for suffix. Whenever we on this number, let's say, we don't care what is the suffix of 5, 6 or 4, 5, 6. These suffixes we don't care about. We are interested specifically in the suffix 3 times 4 times 5 times 6. So maybe somehow we can eliminate the array and use just variable. So with the prefix it's pretty easy. We can just, while traversing the array from left to the right, we can maintain the prefix and update it every time we calculate some element. So let's say we're starting from index 0, our initial prefix would be 1 because there is nothing else to the left. Then we are going forward and we are updating our index with the previously calculated value, which is 1 times 1 equals 1 still. Then we move forward again from 1 to 2 and we update the prefix with the previously processed element, which is 2. So 1 times 2 equals to 2. Now our prefix is 2. We move forward again, and meanwhile updating the prefix, 2 times 3 gonna be 6. So for this processed value, we're gonna get prefix 6, and so on. The problem here is that we don't know the suffixes, because to calculate the suffix same way, we should start from the end. And if we start from the end, we will have again the problem with prefix, because for prefix we need to start from the beginning. What can be the solution then? Since we anyway need to create the output array and we don't consider it as our space complexity, we can put our prefixes to the output array. So every snapshot of prefix variable is going to be in our output array. So now let's walk through the algorithm of how we're gonna save the prefix snapshots. So we know for sure that prefix of index 0 is 1 always, because there is nothing else to the left. Prefix for index 1 should be basically previous prefix plus previous computed value, which is 1 times 1 equals 1. Then we move to second index. We know that prefix for the second index should be previously calculated prefix times the previously computed element, which is 2 times 1 equals 2. Then we move forward, same thing applies. Previously calculated prefix times previously calculated value, which is going to be 6, and so on. So with one traversal from the left to the right, we have our prefixes calculated in the response array. Now, since we have our prefixes already done, we can do our optimization with just keeping one variable, but now we can do it for suffix. And again, we know that for the last index, we know the suffix should be 1 because there is nothing else to the right side. So let's pick the last element in the array. We know for sure that for the last index in the array, suffix should be 1 because there is nothing else to the right of the array. Let's say we start with the last element. We're going to pick suffix as 1 and prefix as the prefix calculated in our output array, which is going to be 120. We're going to calculate it. 1 times 120 is 120. So we're overriding 120 with 120, which does not change anything. Then we move to the left, meanwhile updating the suffix. And suffix becomes 1 times 6 is equal to 6. Now we are at index 4. We are taking prefix 24 and multiplying it by suffix 6. It becomes 144. Good, we updated it. We move to the left, meanwhile updating the suffix. 6 times 5 equals to 30. Now for the third index, we again getting 6 as a prefix, 30 as a suffix, equals 180. And we are overriding our output with 180. I hope you already got the idea. When move like this up until the first element in the array, and for the first element in array, we would have our suffix correctly computed in variable and prefix correctly computed during the first traversal. This way, if we don't consider response array as a space, it takes constant space and it is still all one-time complexity. So with this optimized algorithm, the response array would contain snapshot of variables. It is not exactly the prefixes, but it's rather snapshot of prefix variable. If we would decide to do the same trick as we did with suffix, just maintaining one variable. So we are putting the snapshot of our prefixes to the response array, and then we are starting from the left and maintaining our suffix, reusing the prefixes snapshots that we calculated before. The time complexity would be O1 because we are traversing array just twice. The space complexity, if we don't consider this output array, will be just constant because we are storing our prefixes in the response array and suffix is just single variable. LeetCode forbade us to use division operation, but I was wondering what would be the algorithm even in this case. So it's pretty simple. We are just calculating the product of all numbers. And we try, while traversing, we try to divide this product by the current number and put the response back. The problem is that we have a bunch of edge cases when you have 1 0, when you have 2 zeros, because if the product has at least 1 0, the product is 0 always, right? Basically what we do here, we just handling all of these edge cases. That's it. Thank you for your attention. Please don't forget to subscribe to YouTube and Twitch because we are streaming weekly, solving LeetCode questions, doing system designs and stuff like that. Also, please don't forget to subscribe to Telegram and Instagram as we are voting there for the next content and what we're gonna do. Also, I'm posting some personal life stuff about working at Microsoft. Thank you very much once again. See you.